Okay, so here's a trig example about finding points of inflection. It's y equals x plus 2 sine of x on 1 revolution of the unit circle. So we're going to have to find the second derivative to find the possible points of inflection first. Derivative of sine is cosine. Second derivative is 0 plus the derivative of sine is negative sine. So it simplified pretty well. That's the second derivative. The possible points of inflection are where this equals 0. So we're trying to figure out where sine equals 0. Well, that's where y equals 0, so right here and right here. So our possible points of inflection are x equals 0. It may be a point of inflection, and well, maybe we should consider it because it's in the interval, so pi and then 2 pi. So since this function is including 0 and 2 pi, I'm going to extend my chart a little bit. I'll show you. We need to figure out if it changes here, and it's possibly will change here. So I am going to go maybe from negative pi to 0 here, just to see if I need to see if it changes. And here I'm going to go one more pi, so 2 pi to 3 pi. Just because it has a possible point of inflection at every single pi. So the second derivative at negative pi over 2. That would put me right here. And that's between negative pi and pi, or negative pi and 0. That would put me here. Sine is negative here because it's y, and then negative times a negative, because sine is negative, is a positive. So we're concave up. From 0 to pi, I'm going to use pi over 2. Sine is positive here, so we have a negative times a positive, which is negative, concave down. From pi to 2 pi, I'm going to use this again, except now this is going to be 3 pi over 2, but it is the same as negative pi over 2, so it's the same as this, so it's concave up. And you can see the pattern here. This is going to change every interval. 2 pi to 3 pi, well, this is 2 pi, that's 3 pi, so we're here again. So that's what is it, 2 pi is 4 pi over 2, that's 5 pi over 2, which is the exact same thing as 1 pi over 2, that's negative concave down. So according to our chart, it changes concavity really at every single multiple of pi. So in this interval, we're going to use points of inflection. We're going to call them 0, comma, pi, comma, and 2 pi, comma. But if we're expanding this interval, it's every single multiple of pi, 8 pi. Even. So here's what we're plugging our values back into, x plus 2 sine to get the y values. Now, sine of all of these is always going to be 0, so that's a little bit of a help. We just have the value of x. So if you plug in 0, you're going to get 0. If you plug in pi, you're going to get pi plus 2 sine of pi, which is pi, and so on. and 2 pi. And then if you expanded it, even if you wanted to include, say, 28 pi, it would be 28 pi, comma, 28 pi. Interesting. So let's look at this graph just to make sure it corresponds with what we're thinking. This is the graph. I'm going to zoom trig because that's what I usually do with trig. And I don't know if that helps much because we're talking concavity. So it's hard to see where this exactly changes concavity, but look here. It looks like 0, 0 would be a change of concavity because it goes concave up to concave down. And then here's the next point where it changes concavity. That looks like it's pi. And then up here it's 3.14. So this is pi because I zoom trig. If you go over to the y, that looks around 3. So pi comma pi makes sense. Just to make sure, I'm going to second count, get the value at pi. So you see here's pi, and it says the value at pi is 3.14. So yeah, that looks really, really good. That looks like a inflection point. So pi comma pi does look to be correct, and you'll find out that everything else is correct as well. So that was an interesting one.